Okay, so here's an example. It's available on my website. Um, and you can see, don't be too concerned about the frequency plot yet. That's going to be our next exam block. But this time plot, this is our h of t. And these are where the poles and zeros are. And if you don't like a zero, you can just drag it off, drag off the x too. So now, if you've got no zeros and no poles in our s-plane, our h of s has to be 1. And it does nothing. And what you get out is what you put in. So if its impulse response then will be if you put in an impulse, you'll get out an impulse. So that kind of makes sense. Now let's add a pole to it. So I'll click our pole. So now we've got one pole and it's at 0. So that's the equivalent of having a transfer function that's 1 over s. And if it has a transfer function that's 1 over s, what's the inverse Laplace transform of 1 over s to find its h of t? Who have I not called on? Aiden.
That's just going to be a unit step function.
And that's unit step function. So we've got our unit step function now, and that makes sense. Now here's something kind of cool. When I was an undergrad, I wondered 1 over s plus 1, that looks like this, right? And we know 1 over s plus 1 has a decaying exponent. It looks like e to the minus t. And I wondered, as we get this thing closer and closer to the origin, we've always got an e to the minus something as an impulse response. This is e to the minus 1. This would be e to the minus 2. This would be e to the minus 1/2. But it seems to suddenly flip instantly once it gets on the origin to just plain old u of t. How does that happen? And now when you look at it smoothly, you can see that in the time domain, it just gets longer and longer response until finally it just naturally snaps to 0. And then if you move it to the right, in the right half plane, it's gone unstable. And you can see that anything in the right's unstable, whether it's off the axis and it's oscillating or it's on the axis, no matter what it is, it's unstable. And by the way, just to show you the frequency thing, as we move it higher and higher, you can see the frequency goes up. If we snap it to the axis, firstly, you can see they form complex conjugate poles now. And now you've got this impulse response that clearly oscillates. The more the impulse, the imaginary part, the faster it oscillates, the slower the oscillation. It is true that if it's real, it's not going to oscillate, and the further we move it to the left, the faster it decays. But watch what happens if we snap it off the real axis. So now you can see that it oscillates. And the further to the left we move it, the faster those oscillations dampen. And if you move it slightly to the right, now it'll still oscillate and it will grow with oscillation in time. Let me just see if there's anything else that's kind of interesting. Yeah, I'm going to take away the frequency response just for a moment. There we go. So this is what we've studied so far. So it all seems to be dependent upon the poles, right? Because if it oscillates, then what would adding a pole do? Does that change it from oscillating? Well, it does do some stuff, but it doesn't. The fundamental thing is that whether or not it oscillates doesn't matter on if it has poles. It doesn't matter if it's got poles on the right plane or the left plane. If it's bipole doesn't matter if those zeros are in the right plane or the left plane. All that matters are the poles. If the poles are in the left half plane, it's stable no matter where these zeros are. And no matter how many zeros we have, we can keep adding zeros all over the place. Still, it's decaying away. And the number and the position of the zeros matter much less. Don't matter at all if it's bipole, don't matter at all if it oscillates or not. Does not control at all how fast it decays. It's all a function of where those poles are. Any questions on that? That was a lot of stuff.
I have a question about the calculating it. You said you got to convert the h of s. I'm not sure if we're going to do that in this class or if we'll do it later, but I was curious about that.
Calculate h of t, how to go from left to right?
No, so when you put down like on your other slide, you had a giant fraction, and you said to convert the fraction to like a similar looking fraction with s's and
Yeah.
e's and z's. Are we going to be doing? I guess so that we're just taking because I noticed here at the end you added like an addition sign. If that's what that is.
Down here?
I wasn't sure from yes, sir.
Well, it just means that h of s is always going to be a ratio of polynomials. Every h of s you've ever seen has been always a ratio of polynomials. So all I'm just saying is now if you want to create your S-plane plot, you got to find the zeros of the numerator and the zeros of the denominator. And the easiest way to do that is to factor them. And then once you've factored them, then you've found the zeros of the numerator, you've found the zeros of the denominator. You've done this already, is what there's this actually is not a new technique.
Right. I just wasn't sure. Okay. I think I understand. Yeah, I think I was making it a little more complicated in my head than I needed it to be. Thank you, sir.
Yeah. So the every h of s we've studied so far has always been in this form, and so you just need to find you just need to factor the numerators, and those will be zeros. Factor the denominator, and those will be the poles. And you're right. This does look like a weird form, but all that's trying to say is it's just the factored representation.